You're not in the. Oh, okay, pretty cool basically. But do you get enough time to basically, check, write them? Like it's a huge amount of note. Okay, if you can, no problem. It's up to you basically. It's up to you. So either ways, you will get the recording. So you can just check the recording later and do it as well. It's up to you. Now, the next part that we need to check out is very important, and that is of course this one down here. Okay, so first of all, here the formation of a race mate with SN1 mechanism. Do you know what is SN1 and SN2? Did they teach you? Yes, exactly. No, I'm telling what is specifically what is SN1 and SN2. Nucleophilic. Yes. What is the meaning of SN1? Do you know? And what is the meaning of SN2? Unimolecular nucleophilic substitution reaction. This is bimolecular nucleophilic substitution reaction. So you can clearly understand both of them are of the same mechanism. It's just that this is unimolecular and this is bimolecular. Why bi? Why why uni? Well, if I provide you a table of differences, then it will be much more easier. Wait. So this is the important part, and I think you should write it as well. Do you see it down here? This is the three differences basically. Okay, so in SN1, it depends only on the concentration of the substrate. Okay, I think have you guys, did Shubhrabai teach you the rate equation in the rate chapter? Did they? Maybe not, right? Okay, so there is in the rate chapter we will get to know what is rate equation. So and there is a thing called rate determining step. Okay, so in the one thing that you need to understand that SN1 mechanism, it depends on the concentration of the substrate. Substrate is what? Substrate is basically the reactant. Okay, the reactant which is basically undergoing the mechanism. But another thing that you need to see in SN2, the SN2's mechanism, like basically the progress of SN2 mechanism, in other words speaking, the rate basically depends not only on the substrate's concentration, but it also depends on the nucleophile's concentration as well. So this means what? If both of the concentrate, like if the substrate's concentration decreases, but let's say the nucleophile's concentration increases, the rate won't be affected. Am I clear? But in this case, only the substrate's concentration is affected, affects the rate of the reaction. Okay, that means if there is a change in the nucleophile concentration, it won't affect the rate. Did you understand what I'm trying to say? The difference in SN1 and SN2. Now, if I talk about the mechanism, it is a two-step mechanism. All right, the carbocation is formed first, and then the nucleophile attacks. But in the SN2, it is a one-step mechanism. Okay, nucleophile attacks as the leaving group departs. So basically, what they are trying to say here is in SN1, the carbocation forms, and then the nucleophile attack happens. Then, but in SN2, the nucleophile directly attacks. Okay, we'll get to see the mechanisms, and it will be much more easier. Uh, Next, we have stereochemistry. Again, you know what stereochemistry I've told you. So again, in terms of stereochemistry, this SN1 leads to the production of a racemic mixture. All right, racemic mixture means what? There will be no optical activity, will it? But SN2 results to the causes inversion of configuration, meaning, in other words, optical activity is seen. Am I clear? So what they're trying to say is that SN2 leads to the production of either a dextro or a levo rotatory enantiomer. Am I clear? Depends on the scenario, but what I'm trying to say here is that if any one of them is produced in SN2, there will be optical activity, right? That's what I'm trying to say. But here, a racemic mixture is produced, and you know what's a racemic mixture and why it does not produce, why it does not show optical activity. Did you understand the differences? All right, so please write them down. Now, we will go for the no. Before we do, I mean, did they show you nucleophilic substitution mechanism? Do you know what is it? Okay, then let me show them show that one first. Even though they have this was taught in AS though, if I'm not wrong. It's a fundamental thing. No, I will show, no problem. I'll just give a small revision. I mean, it will be much more easier. Okay, first of all, you know what's a nucleophile? I don't think I have to explain what is a nucleophile, right? What is it? Tell me what is a nucleophile? Which has lone pair of electrons. Exactly. Are these nucleophiles? Mm-hmm. Are these nucleophiles? Yes, they are nucleophiles. So I think if I show you the SN, if I show you the mechanism, then it will be much more easier. Do you see something here? This is what is happening down here. In this case, your what's it called? The nucleophile is attacking. I think. Wait 1 minute. Oh, there is it. Sorry, the mechanism is provided here. This is much more easier. No need to show that. That is a. I wanted to basically go for the AS way, but never mind. The mechanism is here basically. Check this out. Here, look at the formation of a racemate or a racemic mixture in SN1 mechanism. So what did they say here in SN1? A little while back we saw the differences, right? At first, what happens? The polar bond breaks, isn't it? The polar CX bond breaks. You know what CX, right? What does X stands for? Any halogen. Am I clear? And if I show you why it does, then it's because of this. This is the CX bond, okay? The X could be any halogen. In this case, they have shown bromine, but it could be halogen, any halogen. See, this is the polar bond, and due to this polar bond, the carbon will have a partially positive charge, while the halogen will have a negatively charge. Okay, and since the carbon has a lower negativity, while the halogen has a higher electronegativity, look, did you understand why it's a polar bond? It's first of all, it's due to the electronegativity difference. Second of all, there is partial positive and partial negative, all of this which contribute to the bond being polar. Okay, now since it's a polar bond, what's going to happen when the bond breaks? Who's going to take out the bonded electrons? The higher electronegativity one or the lower electronegativity one? Obviously the higher electronegativity one, isn't it? And that is what is happening down here. See, this one breaks down. The Br first breaks away from the haloalkane to form what? To form a planar carbocation intermediate. See, a carbocation is produced. I don't think I have to explain what's a carbocation. You do know what's a carbocation, right? Hello? Yeah, you know what's the carbocation. So, in the carbocation, you can clearly see which carbocation is this. Is this a secondary or a third degree carbocation? You tell me. Is this a secondary or a third degree carbocation? Yes, exactly. It's a secondary carbocation. Can you tell me how did you came to this answer? Because you can clearly see the carbon which has the plus sign is attached with two other carbons, isn't it? Exactly. So the carbon, since it is attached to two other, again, I wanted to provide. Can you add another difference if you don't mind? Another difference is priority. This is much. It should you should remember this priority of carbocation. So this is the priority for SN1. It is going to be third. Okay, 1 minute. Okay, so this is the priority, and for this one it is the opposite. Am I clear? So what I'm trying to say here is that third degree carbocations are more likely to go towards the SN1 pathway, and 1 degree carbocations are more likely to go through the SN2 pathway. Am I clear? Hmm? Okay. So if we just now move on, so see what is happening down here. And now, did you notice another thing I told in the here? Second degree carbocation have 50-50 chance. Like they can either go in SN1 and they can either go in SN2. Okay. So in this case, what is happening? It is going in the SN1 mechanism. So see, check this out. So what is happening down here? The carbocation is produced, and after the carbocation is produced, now this is the unstable state, isn't it? It needs to go to the stable state. In that case, our OH minus attacks it. This is what? It's a nucleophile, isn't it? The nucleophile. Now this is where the racemic mixture is produced. Now the first condition has been already completed. What is the first condition for producing the racemic mixture? We saw, sir. What was the first condition for producing racemic mixture? It has to be a trigonal planar reactant, isn't it? And the second condition was what? The nucleophile needs to be approached, it needs to approach from both sides. So what is happening down here? It is already a planar carbocation. Basically it's present, it's in a trigonal planar shape, isn't it? Done. That's one condition gone. The second condition is what? The attacking species can attack it from the bottom, or it can also attack it from the top. Okay, they did not show here, but you can understand. If it attacks from the top, then it will produce this. If it attacks from the bottom, then it's gonna produce this. Am I clear? A racemic mixture will be formed, which will obviously not show any optical activity. All right, so 50% of labo and 50% of dextro. Yes, that's the reason why it's called racemate or racemic mixture. Am I clear? And I think you understood why optical activity is not so. So SN1 leads to the production of this racemic mixture, but in SN2, check it out. In SN2 mechanism, no intermediates are produced. And again, look, remember in the difference what I said, SN1 is a two-step process. See, it's a two-step process. The first step and then the second step, isn't it? In the first step, what happened? Carbocation was produced. In the second step, what happened? The species attacked, isn't it? But check out in the SN2 mechanism. See, directly at the first step, this guy attacks. All right, to the carbon, to the CX bond, basically with the carbon, which is the halogen. And this, what happens is that this, when this attacks, this basically causes a domino effect. So basically, this causes this bond to break down. And what is happening is that as this comes, attacks, this bond breaks down and C gets a chance to produce bond with this OH. Alright, so this is what is happening here. This part is known as the intermediate stage. Okay, this part is known as the intermediate stage. This is the bond making, this is the bond breaking part, and this is the bond making part. Sorry? Yeah. Yes, in the SN2, it's a one step process, right? So directly at first, we can clearly see the attacking species attacks the CX bond. This basically causes a domino effect. You know what's a domino effect, right? You know what dominoes, right? Like, if you know what I mean. Like, if you break তুমি যদি একটা domino ফালাও, then all the dominoes fall down. So something like that. What I'm trying to say is that due to the OH attacking the carbon, this basically causes the CBr bond to break down. Basically the Br comes out, okay, by taking out the bonded electrons, and as a result, what happens? A vacuum is produced. Basically no carbocation is produced, but instantly the carbon basically produces a bond with OH. Now since it is produced instantly, and since the bond is broken instantly, that is why it is shown in this way. Am I clear what I'm trying to say? No carbocation is produced in the unlike in SN1. Did you understand? Okay, so this is the bond breaking and this is the bond making. So intermediate stage is basically a type of stage where bond breaking and bond making takes place, at a fraction of a second. Eventually you get this. Now this is not a racemic mixture, you can clearly see, because obviously this is not a trigonal planar, and secondly of all, the attacking species just does not attack it from both sides. Am I clear? Okay, so that is what SN2 and SN1 is. All right. See, this was okay. By the way, another question: was this second degree or third degree? This was also second degree, isn't it? So, like I said, second degree carbocations are a I mean, sorry, second degree. What's it called? Compounds or carbons are basically a little bit tricky, considering they can either go in the SN1 way or SN2 way. And when this type of questions come, they will provide you clue in the question. Other than that, if it's a third degree, then it's SN1. If it's 1 degree, it's going to be SN2. Am I clear? Okay. All right. That's gone. That's gone. See, check this out. A racemic mixture can also be formed in the AS reaction of the electrophilic addition of HBr to an unsymmetrical. I think you have learned this in AS chemistry, isn't it? Electrophilic addition. Do I have to show it again? So what happens in the electrophilic addition? The alkene bond breaks down, isn't it? Now, if the alkene is unsymmetrical, we all know what's unsymmetrical, right? For example, propene is unsymmetrical, isn't it? But what about what's it called? Isn't this unsymmetrical? Yes, and this is also unsymmetrical. So if the alkene is unsymmetrical, addition of hydrogen bromide can lead to isomeric products. Okay, say for instance HBr. Okay, it's the typical electrophilic addition first step. What is happening? The electrons present in the alkene or the carbon to carbon double bond causes this bond, causes the Br to break down from HBr as the whole thing approaches towards it or comes near it. Okay, as a result, what happens? The Br breaks down. Now when the Br breaks down and this bond breaks down, what happens? A carbocation is produced, isn't it? Now the Br has chance to attack it from the top, or it could even attack it from the bottom. Okay, in both ways it can. And so I mean, one thing, for producing the racemic mixture though, you need to understand one thing, that is, uh, if the carbocation produced is in planar shape, only then a racemic mixture can be produced. All right, because like I said, uh, there are two things, like either what's it called, the racemic mixture that you see down, I mean the planar shape that you see down here, it's not all the case that the planar shape might be present. Am I clear? There are some certain conditions in which this planar molecule is produced, and when this planar carbocation is produced, bromine can attack in both sides. It could attack from the top or it could attack from the bottom, eventually leading to this. Am I clear? Otherwise, it's just the normal way which you have learned in AS. Am I clear? Okay. So I hope you understood. Okay. Now, uh, okay, 5 minutes break. I'm coming. 2 minutes. Okay. All right, are you there? Let's start. So the next part is basically carbonyl compounds, aldehydes and ketones, which we have seen already, quite a few. It's just basically from the basics they're gonna show. That's it, nothing else. Anyways, you know what carbonyl compounds are, right? Basically compounds which consist of this functional group, right? No biggie. So now there are two types of carbonyl compounds. We have aldehydes and then we have ketones. So what are aldehydes? Aldehydes are, these are aldehydes. These functional the compounds which consist of this functional group. These are known as aldehydes. Okay. And if the carbonyl compound is on the end of the chain with an hydrogen attached, it is an aldehyde. Like, I mean, they're provided in wording, but again, you can clearly understand. That's it. Then if I talk about this part, if the carbonyl compound is in the middle of the chain, for example down here, then it is a ketone. The name will end in "-one". All right, so that's how it goes. If I talk about the solubility in water, the smaller carbonyls are soluble in water because they can form hydrogen bonds with water. This is important. Just wanted to let you know that basically what they're trying to say is that longer chain aldehydes or longer chain ketones are more soluble in water. The reason because is that they can produce what? Hydrogen bonds. Sorry, I think I no told the opposite. Sorry, I told the opposite. So shorter chain carbonyl compounds, or in other words, shorter chain aldehydes or ketones, they have chance to be more soluble in water because solubility depends on what? The production of hydrogen bond, isn't it? So if it is short enough, won't it be much more easier for water molecules to reach and produce hydrogen bond? And what's the condition for prerequisite for producing a hydrogen bond? We require hydrogen, right? We require hydrogen, which we are getting from water, and we are getting we need what? More electronegative element than hydrogen, isn't it? In this case, what is that? Oxygen, right? Are we getting that? Yes, we are. We are getting the oxygen from the carbonyl compound and we are getting the hydrogen from the water molecule. All right, so that is what solubility is. Another thing, pure carbonyls cannot hydrogen bond, but bond instead of by permanent dipole-dipole bonding. What they're trying to say, okay, I'll explain this a little while later. Uh, Reactions of carbonyls. The carbonyl bond is polarized because O is more electronegative than carbon. The positive carbon atom attracts nucleophile. Okay. First of all, why is that the case? First of all, how do we distinguish whether a bond is polar or non-polar? Okay, do you know that? Look, first of all, we tend to understand whether a bond is polar or non-polar by checking out the electronegativity difference. Do we have electronegativity difference here? We do. Oxygen is more electronegative than carbon, right? So there must be a significant electronegativity difference, right? So if that's the case, we are kind of sure that partial charges will be produced. The second condition. So both conditions are met. As a result, this bond is polar. Am I clear? So the carbon is partially positively charged and that is negatively charged. All right. And since nucleophile here is our negatively charged, so we know positive, unlike charges attract, and you can clearly see the negatively charged nucleophile gets attracted towards the partially positively charged carbon. All right. So that's why carbonyl compounds are vulnerable to nucleophiles. And we saw that a little while ago in SN1 and SN2 mechanism, right? We saw that these are what where is it? Sorry, oh, we'll see it later, but you will see this. Due to them being vulnerable to nucleophile, these carbonyl compounds also undergo SN1 and SN2. Am I clear? Okay. In comparison to the carbon to carbon double bond in alkenes, the carbon to the carbonyl bond is more stronger and does not undergo addition reactions easily. Yes, this is also a fact that if you compare this with this, it is more stronger and it's not. I mean, a huge amount more energy is required to break this down and go through the reaction. Okay, oxidation reactions. Okay, these are very important. I think you have learned this in AS as well, right? That when you oxidize primary alcohol, aldehyde is produced. When you oxidize aldehyde, carboxylic acid is produced, right? And when you oxidize secondary alcohol to ketone, I mean, when you oxidize secondary alcohol, you get ketone. And one thing's for clear, tertiary alcohols are not oxidizable. Okay, and what do we use for oxidation? Oxidizing agent, right? Can you name some oxidizing agent? Look, it's provided here, isn't it? Potassium dichromate 6. And this is a catalyst, by the way, not oxidizing agent. Diethyl sulfuric acid. Another condition is heat under reflux. I think you know what's heat under reflux, right? That do I have to show? No, that is acid base. How come there is acid base involved? No, no, nothing acid base here. Yes, this is the color. There is a color change, of course, but that is from orange to green, not from pink to colorless. Okay, dichromate basically is orange in color. It basically goes to green since this basically breaks down and reduces to Cr3 plus ion. Am I clear? And Cr3 plus is green in color, and while this one is in orange in color. Do you understand? Okay. Now, why it's orange, why it's green, I will show this in transition metal chapter because chromium is a transition metal. What we'll talk about it deeply in the transition metal chapter in Unit 5. But then again, you have to understand, you have to understand the color change. Okay, make sure to remember the color change. And this is the reaction. Say for instance, say for instance aldehyde. Okay, you're oxidizing it using Cr2O72 minus and HH plus C. This is produced water and this Cr3 plus, which is the main source of green color. All right, aldehydes can also be oxidized using Fehling solution or Tollens reagent. Okay, these are also oxidizing agent. All right, it's just that they're different. Tollens reagent is formed by mixing aqueous ammonia and silver nitrate. The active substance is the complex ion. So you just have to remember this part. That's it. You don't have to remember the whole thing. For example, check this one out. What were we doing? We're basically reacting with this Ag plus, right? Basically this is coming from here, the active substance, and eventually what is produced when we basically oxidize the aldehyde? What? Carboxylic acid is produced, isn't it? Right? So that is what is produced. And silver H plus. Look, the observation is pretty simple. What is happening here? We are there is silver here involved, not carbon, not Cr2O7. Okay, which is what? Which is what? Silver in color, right? So there won't be any change considering silver's color does not change. It's the same. Am I clear? That's what I'm trying to say. Nothing else. And if I talk about failing solution, in case of failing solution contains what? It contains Cu2 plus ions. All right, and now we know Cu2 plus ion is blue in color. So what? Look at the reaction. When it reacts, what is produced? Cu2O, right? Like Cu plus is like from Cu2 plus to Cu plus. Now we also know that Cu plus is a different color. Like Cu plus is a different color and Cu2 plus is a different color. This is blue in color. So since Cu plus is produced here, see, did you understand? This is red in color, and that is the reason why we tend to see the blue solution changing to a red precipitate. The Cu plus is found in the solid form. That's why it's a precipitate. And ketones obviously do not react. So that is what Fehling solution do. So the difference is pretty simple. What is the difference? The difference is pretty simple. Even though both of them produce the same carboxylic acid, the difference is what? Color change. Am I clear? Nothing else. So did you understand? Hello. Okay. So make sure to read up to this part. So tomorrow, do you have any time which you can provide me? Okay, okay. Forget about tomorrow. Is it possible for you to give the? Can I take a class on Sunday on night? You tell me which time is suitable for you. Is it possible? You mean evening? Hmm, 5 is not possible. But is it possible for you to at 6? Okay, understood. Okay, so how about what's it called? Okay, is it possible on Monday then? Monday, Monday 5 p.m. Is it possible? Okay, so Monday 5 p.m. it is. All right. All right. So Monday 5 p.m. will be our our compensation class. Already I have taken a compensation. I'll take another compensation class. We are supposed to take two classes this week, but unfortunately, you did not join. Actually, you did not know, I guess, right? But I provided the schedule that day. You should have joined. Okay, it's okay, no problem. And I think there is another guy who tends to join as well, right? With you, like his name is Rakshit, basically. All right, so please tell him in the group to join from next class. Okay. Oh, okay, okay. So he will join later, I guess, after coming from USA, right? Ah, I see. Okay, no problem. Then that is fine. Is he Indian? Okay, fine. All right. So fine. That's it for today. Then we'll meet at Monday, 5 p.m. See ya. Is he Indian? Oh, sorry. Oh, I mean, Indian. Rakshit, oh.